Welcome to the last lecture for Chapter 13 as we wrap it up with freezing point, boiling point, and osmosis. Although we may not be familiar with it in California, when there's lots of snow or ice on the road, the common practice is to sprinkle salt on them. And that's because salt lowers the melting point of ice. Okay, so anytime you have a salt and water solution, it's going to remain in a liquid form even below 0 degrees Celsius, which is the regular or normal freezing point of water. So if we add salt to it, it's going to freeze at below 0. In fact, this happens not to just salt, but to any volatile solute. So if we have water and you've got any non-volatile solute, anything that does not evaporate easily, it's going to extend the temperature range over which the liquid remains a liquid. So it's going to allow that liquid to freeze at lower temperatures, and it's going to make that liquid boil at hotter temperatures. And this is what we call a colligative property. Okay, so a colligative property is one where it actually only depends on the number of solute particles in the solution, not the actual type of solute particles. So whether we pour in, whether we put on the sidewalk, for example, 2 grams of salt or 2 grams of sugar, it's going to do the same types of things. It's going to lower the melting point of water. So let's talk about this freezing point. A freezing point of a solution containing any non-volatile solute is going to be lower than the freezing point of that pure solvent. So just like we said, we sprinkle some salt into water, and that water is now going to freeze at a lower temperature. The more concentrated the salt is, the lower the freezing point becomes. So if you add more salt, it's going to lower the freezing point even more. Now this happens because of this picture. Well, this picture doesn't happen because of the picture, but this picture down here shows what is happening when you introduce any non-volatile solute. So in regular freezing or melting point, you're going to hit a temperature where the intermolecular forces between the water molecules are going to start to kind of break away apart from each other, loosen up. Well, so that's here. So this is pure. Now, if we have one where there is some solute in it, okay, like this side, then what we're going to have is the intermolecular forces not being able to break away as easily. Okay, so we're going to get freezing or melting at a lower temperature than pure. Now, when we talk usually about freezing point depression, it's called, because it lowers the freezing point or depresses the temperature at which something freezes, we usually talk about the solute in concentration of what's called molality. And it's one letter away from being molarity, but it's not, it's molality. And it's represented as a lowercase italic m. All right, and molality is the number of moles of solute per kilograms of solvent. We can see that here. Moles of solute per kilogram of solvent. So let's take a look and see how that works. Actually, before we do that, over here in this picture is a picture of antifreeze. Okay, antifreeze is a solution that has, actually it's called ethylene glycol, is the solute that is dissolved in water, and it is poured into cars' engine part, I believe, in order to keep the water, inside from freezing. So it's called antifreeze because it does not allow water to freeze at the regular point. It's going to lower the amount of water. It's going to lower the amount of temperature that the water starts to freeze. So if you live in really cold parts of the world, you can pour an antifreeze and your car will still start. in the morning, even though it's been sitting out in the cold all night. Okay, so the more concentrated the antifreeze, the lower the temperatures it can withstand. So actually, if you live in areas where it snows in the winter, you have different antifreeze that you put in during the winter versus the summer. Or that's how it used to be. Now I'm sure there's a one antifreeze that will go the entire range, without having to actually flush it all out and get new ones. Okay, so let's take a look at this molality. Moles of solute divided by kilograms of solvent. And here's an example. It says calculate the molality of a sucrose, C12H22O11, solution containing 50.4 grams of sucrose and 0.332 grams of water. All right, so we're given here the grams of sucrose. Okay, and we notice that in our equation we have to actually have moles. So the first thing we got to do is change grams to moles. Okay, so 12H22O11. Let's change that over to moles of it. And what we got to do is look on our periodic table to figure out what is the molar mass of sucrose. And that is 342.34 grams. 342.34 grams in 1 mole. So what we're going to have is 50.4 divided by 342.34, which is 0.147 moles. 0.147 moles of sucrose. So now we can actually plug it into this equation up here. We could go 0.147 divided by, and our kilograms were given, 0.332. And what we'll get is 0.443 molality. Okay, so 0.443 and then little m. Okay, so that is the concentration in molality for this sucrose solution. Here's an example that you can try on your own, and I have the answer right there for you. So calculate the molality of a solution containing 17.2 grams of ethylene glycol. So this is an antifreeze solution that is dissolved in 0.500 kilograms of water. So what you'll do is you will use your molality, which is moles of solute divided by kilograms of solvent. So go ahead and do that on your own and check your answer right down there. All right, so guess what? We can calculate everything. And so we can calculate the freezing point, actually, of a solution that is lowered by a particular amount of solute using this equation right here. Okay, now these F's are supposed to be little, subscripts there. So the change in temperature of the freezing point is going to be the molality times what we call a constant. All right, so Kf is the freezing point depression constant for the solvent. And for most solutions that we are going to deal with, most if not all solutions we're going to deal with, it is water. Water is the most common solvent for solutions. So here is the Kf for water. It's 1.86 degrees Celsius times kilograms solvent divided by solute. Okay, so the numbers here, though, is what's important, 1.86. So that's going to be our constant that we're going to multiply the molality with to find the change in temperature. So the change in temperature for the freezing point. So let's see how this works with an example. Calculate the freezing point of a 2.6 molality sucrose solution. All right, so again, we're going to use this equation, m times Kf. Okay, super easy. Here's our molality, right? And we said the Kf for water is 1.86. So what we get is 2.6 times 1.86, and that's going to be 4.8 degrees Celsius. All right. So the change in freezing point is going to be 4.8 degrees Celsius. So that's the difference. So their actual freezing point is going to be negative 4.8 degrees Celsius. Here, negative 4.8 degrees Celsius is what this solution is now going to freeze at with this sucrose added. All right, and here's one that you can try on your own. Calculate the freezing point of a 1.7 molality ethylene glycol solution. So what temperature is it actually going to freeze at now? And so hopefully in your calculations, here's the answer so you can check yourself to see if that is correct. All right, so like we mentioned earlier, if you add a non-volatile solute to a solvent, you're going to extend the temperature range at which it remains a liquid. So that also includes boiling. The boiling point of a solution containing a non-volatile solute is going to be higher than the boiling point of a pure solvent. And the reason why this works is that here's an example of a pure solvent here, or we have nothing but water molecules, and so we're going to get evaporation and condensation above the above the liquid line that we've talked about previously. But if we add little solute crystals in there, basically they get in the way of water evaporating. They're going to be trying to hold on to those water molecules and not let them escape into a gaseous form. So that's the science behind boiling point elevation, we call it. It's going to, so therefore it's going to need more energy to get those water molecules from a liquid to a gas. Now, just like everything else in chemistry, we can quantify that. And so here is our lovely equation. It looks just like the other one, except it has B's for boiling point instead of F's for freezing point. So the change in temperature of boiling for a solution is going to be equal to the molality times the boiling point elevation constant for the solvent. And just like last time, that constant is going to be for water, because water is the most common solvent. So for the boiling point constant for water is 0.512 degrees Celsius. So let's take a look and see how this actually works. Alright, so here's an example. Calculate the boiling point of a 3.5 molality glucose solution. So let's use our equation. The change in temperature for boiling point equals molality times the constant. So molality here is 3.5 and the constant is 0.512 degrees Celsius, basically times molality. You're funny. So if we calculate that, that's going to equal 1.8 degrees Celsius. So what that means is that the water is, or the solution is going to boil 1.8 degrees Celsius above the boiling point for regular water. So our boiling point then is going to be, if regular water boils at 100 degrees Celsius, this boiling point is going to be 101.8 degrees. Okay, so that's our final boiling point. So again, here's a one for you to try at home. Calculate the boiling point of a 1.7 molality ethylene glycol solution if the actual boiling point of pure water is 100.00 degrees Celsius. So plug it into that equation and see if you can get that answer. The last thing we're going to talk about when it comes to solutions is osmosis. Why drinking salt water causes dehydration. So you're out in the ocean, on a boat or playing in the ocean, and you get thirsty and there's water all around but not a drop to drink. because it's all salt water. Salt water is going to cause dehydration because of osmosis. Osmosis is the flow of solvent, and in most cases, that's water. So the flow of water going from a less concentrated solution to a more concentrated solution. So if we take a look at this picture here, we've got, kind of in the pre-solution, all right, the original, we have two solutions that are divided by what's called a partially permeable membrane, or semi-permeable membrane. It allows water molecules through, but nothing bigger than a little water molecule. So if we had a concentrated sugar solution on the left and a diluted sugar solution on the right, what happens is that water moves across, goes from high concentration of water to low concentration of water. Or another way to think about it in terms of solution, it goes from the low concentrated solution to the high concentrated solution. So in either way, we're going to get water going from the right to the left. And so over time, the amount of water is going to decrease on the right-hand side and is going to increase on the left-hand side, because water is flowing over where there's more solute particles. And it's going to continue to do that until it hits a particular osmotic pressure. Osmotic pressure is the pressure required to stop, I should say stop, to stop the osmotic flow. So it's the amount of pressure that basically when you reach that pressure, water stops moving from one side to the other. Osmotic pressure is also a colligative property because it just depends on the concentration of the solute particles, not on the actual types of solute particles. So you could have salt in there or sugar in there, and it's not going to affect the osmotic pressure. It's just how much of it you have in there. So more concentrated the solution, the greater the osmotic pressure that will be reached. All right, so this is how it applies to kind of real life situations and why you can't drink salt water. So your living cells, you have membranes that act like semi-permeable membranes. Okay, so it allows water molecules through, but not any bigger molecules. So if you put a living cell into seawater, okay, or if you just imagine drinking seawater, and now you've got seawater amongst the living cells in your body, your cells are basically going to lose water through osmosis. They're going to become dehydrated. All right, so they're going to become all shriveled and shrunken, like this guy here. So imagine this is a bunch of salt water on the outside. Water from the cell goes out. All right, so basically, if you drink too much salt water, you're going to be losing water from your cells into body cavities, and is not going to be a good thing. However, if you put a living cell into pure water, it becomes swollen. So you've heard of those rare cases where people drink too much water and die. Basically, they are exposing their cells to too much pure water, not enough, just the right concentrated water. And so their cells start to swell and can burst if that happens. Because what happens is that water is going to be going into the cell, because the cell now, if you put it in pure water, there's no solute at all in pure water, no ions, no nothing. But your cells inside do have stuff in there, and so the water is going to start to be seeping in to go from high concentration of water to lower concentration of water. So that's what happens. You probably have heard of or studied isotonic versus hypotonic versus hypertonic solutions in biology, where isotonic means equal, hypo means the concentration is less, and then hyper means concentration of solute is more. So that's how it works in living cells. All right, and so that wraps it up for chapter 13 and solutions. We'll see you in class.
Bye.